All right, let's talk about gravity. So what did Newton do? Because they kind of understood that gravity existed before Newton, so that's kind of a misconception. The universal law of gravity, what is it? Basically, we're going to talk about that. Gravitational constant, inverse square law, weightlessness, ocean tides, gravitational fields, Einstein's version, black holes, and universal gravitation. So Newton wasn't the first one to talk about gravity. I mean, obviously, anyone with half a brain figures out, hey, stuff's always falling down. There's some kind of force doing that. And it's probably a legend that Newton figured out gravity by sitting under an apple tree and getting hit in the head with an apple. So that's probably not, that didn't happen. Okay, so in Aristotle's time, there was different ways to view motion. And the motions of the planets and the stars were not governed by the same, in their minds, were not governed by the same laws that of stuff that was going on Earth. Things in space were natural motion. They always consisted of circles, but stuff on Earth tends to go in straight lines. So that they were like, hey, there's different laws for space. So Newtonian synthesis was basically said the same set of laws applied to everything universally. So the law of universal gravitation just simply states that everything pulls on everything else. And it's always attractive. We don't, there's no gravity. Like if you put a north and north or a south and south magnet together, they repel each other. Gravity doesn't work that way. It's always attractive. And it's proportional to the inverse square of the distance between them. What does that mean? So if I do a little annotation, that's a pretty color. So the force due to gravity equals some constant, we'll just call it star for now, times mass 1 times mass 2 over the distance between those two objects squared. That's the universal gravitational law. And I'm done. Let's see. Let me stop annotating. There we go. All right, what's going on with it? Okay, there we go. Do this. Annotate. Here. And then all of a sudden it doesn't want me to, or doesn't allow me to go back. Okay, there we go. Hopefully it works now. Okay, I guess that's how you go left and right. They must have changed something. So there it is. The little proportionality symbol just means that that's another way to write something without putting an actual constant there. So this little guy is the same as saying force equals G mass 1 mass 2 over the distance squared. So you got to consider both objects. So the first object is not the only thing that contributes to the force or the weight of an object. So the Earth example, it could be this guy right here. Then this would be your second object. And the greater the mass, the greater the force. Let's say clear all drawings. Okay, here's our first question. Newton's most celebrated synthesis was and is of. Pick the best answer. Nope. Why is it not clearing? This thing is acting weird today. There it goes. Earthly and heavenly laws. That was the Newtonian synthesis. Only 20% of it got it right. So let's take a look at why it's not the other one. Weight on Earth and weightlessness, outer space. No, that's not the Newtonian synthesis. Yeah, he might have talked about that, but that's not the synthesis. It just means that all the laws are universal. Like the laws that are at work on Earth are the same laws that are at work in space. And it's not masses and distances, not pass and toss rocks. All right, the universal gravitation constant, this guy right here, was something that they did not know until they did some experiments back in the late 1700s. And if you watch the movie, basically I assigned a little movie to watch in the homework set. It talks a little bit about how they found this. And the experiment was called weighing a mountain, or weighing the earth, rather. So what they did was found out how strong the force of gravity was between two weights. And basically by knowing the distance very carefully, knowing the two masses, when they measure the force, they can calculate this. Once they knew this, they can calculate the weight of the earth indirectly. And this is true through the whole universe. So inverse square law pretty much is for anything. Let's see, share anything that decays as you get further and further away. Let's see what I mean by that. Stop sharing. Let's do whiteboard. Okay, so this is the best way to visualize the inverse square law. I learned this when I was a kid. So there's a piece of toast. And I work at a restaurant and I want to put butter on this piece of toast. So let's use yellow for butter. So if I spray butter here, say it takes 1 minute to get a certain amount of butter on that toast. If instead I'm lazy and I don't want to like have to do a bunch of different single toasts single toast one by one, I want to cheat and do 4 at a time. So because of the angle of the spray, I'm going to have to like move the toast out twice as far so that the spray is going to reach all 4 pieces of toast. Now, what can you say about the amount of toast or amount of butter that's landing on the toast per unit of time? Is it the same or is it going to decrease? What do you guys think? Unmute yourself and just shout it out.
Decrease.
Yeah, it's going to decrease because you're thinning it out. You see, like these droplets are closer together than these droplets. So take a guess. How much longer do you think I'll have to hold the butter gun to spray the butter on the toast compared to this first one? How much longer do you think it's going to take?
4 times.
What's that?
4 times.
Did you say 4 times, buddy?
Yes, sir.
Okay, your volume's really low for some reason. Let me make sure
I'm
my,
sorry.
no, it's all right. I had my volume down too. That didn't help. Okay, so yes, 4 times. So 1 time here and 4 times here. And this distance is doubled. So this is, say this is 1 foot. Then from here to here, let me use a different color. So this distance from here to here is 1 foot. And this distance from here to here is also 1 foot. So I double the distance. And if you look at this inverse square law, force equals big G, mass 1, mass 2 over distance squared. What happens if you double the distance? What happens to the force? You're going to square this thing, right?
Decrease by half.
Use a different. Well, that would be the case. That would be the case if there was no square here. But the square operates on both the 2 and the, so after we square it, it's 4D squared. So basically what I'm saying, it's like putting a 1/4 on both sides of this equation. So I'm reducing the force by 1/4. So doubling the distance reduces the force by a 1/4. What about tripling the distance? How much is the force going to be? What's that?
1/6.
It'd be a
It'd be
9.
1/9. Yeah, 1/9, because 3 squared equals 9. If we tripled the distance, we'd wind up with 9, 1/9. So that's the inverse square law. Does that make sense, folks? Yeah, okay.
Yes, sir.
There are all my drawings. Stop sharing. Go back to my slideshow. And there it is, right there. There's my, they're using paint instead of butter. And if you plotted this out on a graph, so if you're right at the surface of the earth and the D represents the diameter of the earth, you get the full force of gravity. But as you get further and further away, you see it drop off and get weaker and weaker here. And so gravitational force is proportional 1/D squared. Okay, so let's check your newfound knowledge. New question is up. The force of gravity between 2 planets depends on their. This should be an easy one. It closes Kurt. You got a glare. You get better video quality now. Nice. 80%. Yep. That depends on the masses and the distance apart. All right. Here's another question. If the masses of 2 planets are somehow doubled the force of gravity on them, pick the best answer. Okay, we're all over the place with this one, so I'll do a re-explanation. So let's write down our equation. Force equals big G times mass 1 mass 2, distance squared. Well, if we double if we double both of our masses, because the question said double both of them, what factor is gonna come out here? What can I factor out? What can I bring out?
2.
Both 2's, so 2 times 2 is what?
4.
4.
Yeah, so it's 4 times what we originally had. So then B would be the correct answer. All right, here's another one. If the mass of one planet is somehow doubled, the force of gravity between it and the neighboring planet, pick the best answer. Corollary question here. That's awesome. So you guys are getting it. Yeah, so there's 2 more folks out there. If you could submit your answer, then I'll. Yeah, perfect. Okay. So very good. So original equation. And that's one of the advantages of coming to lecture is, like, at first you guys are struggling with this question, but now seeing this, being able to sit here and kind of mess with this. So I'm going to double the first mass times mass 2. That means I could bring this 2 out front. So that basically doubles what I had before. I'm used to writing as r squared, so forgive me. But it just means the distance between the 2. So good job, guys. It doubles. So weight. So a weight is equal to mass, the mass of an object, times the acceleration of gravity. And the acceleration of gravity is due to the force of gravity, due to this gravitational constant. So you can also write this would be the mass, big G. Sorry, let me clean that up. Let me do that again. Wonder if I can erase this. No, that's weird. Annotation's not turned on, but it's still letting me draw. But that's cool. We'll just scribble this out. Weight equals big G times mass of the Earth times the mass of the object that you're weighing. And this distance would just be the radius of the Earth. So then, since this right here, let me use, is the same as this guy right here, then all the rest of this must equal little g, which is, remember that from earlier lectures, it's 9.8 meters per second squared, or just to keep things simple in this class, we usually round it off to 10 meters per second squared. So when we multiply the mass times the acceleration of gravity, we get the weight. And this acceleration is not an actual acceleration. We're not actually acceleration. But if you were to drop an object, that's how quickly it would accelerate without air resistance. So another thing to notice is if we start accelerating downwards on a platform like an elevator, if we're standing here, what do you notice about your weight? If the elevator starts accelerating downwards, what do you notice about it?
It decreases. You feel lighter.
Yeah, you get lighter. If there was a scale on the floor, it would get lighter. Now, what about if you start shooting upwards, accelerating upwards in the elevator? What do you notice?
You would feel heavier.
You feel heavier.
Yep. Yep. So basically, since astronauts are not touching anything, and they're basically in a state of free fall as they orbit the Earth, they have the feeling of being weightless. Also, when you start in free fall before air starts blowing against you, you have for a second weightlessness. So your normal weight at the elevator is just sitting still. If the elevator is accelerating upwards, you have greater than normal weight. If the elevator starts accelerating downwards, you have less than normal weight. If the cable breaks, you have zero weight. But the cool thing about elevators is if the cable breaks, there's a mechanism that there's brakes in the elevator that are being held toward the elevator by that cable pushing up. So if the cable snaps, the brakes pop out and catch you. But I know somebody that happened to. I know somebody that of a cable that broke. And it was a brand new elevator. The cable snapped, and the elevator fell about 4 feet before it lodged itself. And she got hurt still, but not severely.
It must have
That
been
was at our high
terrifying,
school.
though.
It was brand new. I know that's got to scare the crap out of you. Snap. All right. Let me reset the question. All right, it's good to go now. When an elevator accelerates upwards, your weight reading on a scale is, pick the best answer. Awesome. Everybody got that right. Raider. Corollary question. When an elevator accelerates downwards, your weight reading is. Nice. Everybody got that one right. Those are easy ones. All right, another question. When the elevator cable breaks, the elevator falls freely, so your weight reading is what? Nice. We're cranking through these. 0. Here's another question. If you weigh yourself in an elevator, you'll weigh more when the elevator. Another corollary. Trickier question. Got everybody. Every single one got tricked. If it's constant motion, do you feel any forces?
No.
Nope. Yeah, Newton's first law, object in motion stays in motion unless acted on by an external force. So what's the only thing that's real change? Acceleration, right? So what's the correct answer?
C.
Yeah, C. Y'all got suckered. Ocean tides. So basically, the ocean tide's pretty simple idea. The moon pulls on the ocean, and you've got a big lobe of water that's following the moon around. So wherever the moon's above, the water level is going to be higher. And I got a story about that. I've been to the place where the ocean tide is the highest in the world. And the reason why it is because the time it takes for the water to fill in the Bay of Fundy is the same amount of time that it takes the Earth to turn under the moon. So it's kind of like pushing somebody on a swing set, right? What happens if you push on a swing set with the wrong timing? Is the person going to start swinging more and more?
No.
No. You have to push with the same time. So in the Bay of Fundy, the moon is pushing at the same amount of time it takes the bay to fill up and fill out and run out. So So it's like pushing somebody very gently, right at the right, right with the right timing. And so the tide goes up and down 50 feet in the Bay of Fundy. So you literally, you could pass by a dock and there's a 50-foot high dock, and the boat is even with the dock. And then you come back 3 hours later and it's sitting in the mud all the way down to the bottom of this 50-foot dock. It's pretty crazy. I had a friend who used to live in Nova Scotia, Canada, and I helped him move. I flew out there, and I think that I saw that when I first got there. It's like, look at this dock, and then like later we drove past it, and it was like the water was all gone. It's crazy. So high tides occur every 12 hours. So sorry, I said 3 hours. It's actually 6 would be the difference between low and high tide. Now, sometimes you can get the sun and the moon pulling in the same direction, and that increases the effect. The moon causes bigger tides than the sun does, but when they're both pulling in the same direction, we call it spring tides, and they're higher. The neap tides is the opposite, is when the moon is perpendicular to the sun. The two lobes kind of cancel each other out, so those are actually lower than normal tides. So gravitational field, gravity is a field force. What does that mean? It's something that causes action without actually touching. So electricity is an example of a field force. Magnetism is an example of a field force. And gravitation is an example of a field force. And so the lines of gravity are pointing into the earth. So if you drop something, it's going to follow those charge. If you had a charge, it would be attracted to a negative charge. A positive charge would be attracted to a negative charge. My laptop's complaining that the battery's about to die, so I'm going to pause the recording. That's funny. Okay, so gravitational fields increase as you get closer to the surface of the earth. And then what if you were to burrow yourself to the core of the earth? What do you think would happen to the force of gravity? You think it would affect it as you got toward the center if you had a special suit to prevent yourself from burning up? What do you guys think? What would the gravity be like at the center of the earth?
Would it be the same?
Stronger?
Stronger? Well, what direction would it be pulling if you were at the center of the earth?
Towards the center, right?
Well, you're at the center.
So would it be 0?
Yep, very good. So if you're a little, let me draw a little stick figure. If you're a little stick figure here, this part of your body is getting drawn in this direction. This part of your body is going this direction. This part of your body is going this direction. But it's weak too, because only the mass that's underneath you or that's closer to the center is the only mass that's attracting. All the rest of this mass out here, so this piece of mass of the earth is actually pulling on you. It's trying to pull you back to the surface. And you got this mass over here that's trying to pull you, and all this stuff cancels out. So as you get closer and closer to the center of the earth, see this little graph here? It drops off linearly. So this is the 1 over d squared right here, this part. But this is force is proportional to the distance. So as you go further out, the force increases proportionally. So this is a totally different equation. That's because you're losing all this mass. And you can, this is just like if you had a weight attached to a spring. This follows a law called Hooke's law, which the force is proportional to the displacement. So if you have this distance here is x, and this makes sense. The more you pull a mass, the more the spring resists you. Well, what happens if you take a mass and you let it go and you stretch the spring and you let the mass go? What's going to happen to it in this little situation here? Does it shoot back up? If you pull the mass down, stretch the spring and let it go, what's going to happen to the mass?
It'll shoot back up.
It'll shoot back up. Will it stop at the place that it was originally resting before you pulled on it, or will it go past that point?
It'll go past it.
Yeah, it'll come up here. And then now gravity's got it, and it needs to try to restore itself, so it'll fall back down. But it's going to have all this kinetic energy, so it's going to go past. So it ends up going up and down, up and down. So the thing just bounces like this. Well, this is a linear relationship. So if you double the displacement, you double the force. Well, if you go back to this, let's see. That's weird how this, there it goes. So this is also a linear relationship. If you double the distance, you double the force. So if you graphed out the spring on the mass, it looks like a sine wave like this. So this is time. And this is displacement over here. So what do you think if you cut a hole through the earth and a person dives in, what do you think is going to happen to the person? What do you guys think? You think they're going to stop at the center because gravity is zero?
They'd keep going, right?
Yep, they'll keep going. So all this momentum, they're going to keep going, but what's going to happen when they get to this other side right here? What do you guys think? Are they going to keep shooting off into space, or what do you think is going to happen?
They'd stop. They start getting pulled back the other way.
Yeah, exactly. They start getting pulled back the other direction. So it ends up being just like the spring over here. The person would go back and forth forever if there's no air friction. So it's like a spring, a mass in a spring. Einstein's theory of gravity. So what Einstein said is that the force of gravity is not really a force. What it is that mass actually causes time and space to get warped in a curved path. So an object, instead of like being pulled, is actually in a bent line because it's traveling bent space. Now I know that's super hard to get your mind around, and it's not all that important for the course because we're not going off into that tangent right there. But and it turns out that, as weird as that idea is, all the experiments that we've done so far seem to point that Einstein is actually correct. Another consequences of this is that these curved space-time, if you disturbed it, like if you had two black holes crash into each other, it would send out waves of this disturbed space-time. And they were looking for years and years and years. They built these things called gravitational interferometers. And basically, this is an oversimplification. You have a laser over here shooting at a mirror over here, and the laser bounces back, and you time it, and you could tell how far this travels. Well, if the Earth passes through one of these warped space-time things, this distance will shrink and expand a little bit. Now, this is not a very big amount. I mean, it's on the order of the size of atoms that this vibration happens, this shrinking and lengthening of this distance. And they have to have all kinds of things to actually isolate it from ground waves. Like, so if a truck drives by like 10 miles away, it would shake this equipment. So they have to actually design it in a way that that shaking doesn't affect the distance, which is very complicated, but they did it. They got it to work. And when I was at Cal State Fullerton in 2015, working on my master's degree, that part of the team there, the physics department, was actually working on doing computer simulations. So they were part of this LIGO team. And they made the discovery finally in 2015. They actually detected the first gravitational wave. And they have several of these things around the Earth, and gravity waves travel at the speed of light. So here's the Earth. So the gravity, what's going on? Well, my screen just went black. Can you guys still hear me?
We can
Yeah,
still
I can
hear you,
still
and
hear
we
you.
can still see the screen on our end.
We can see you changing the slides.
Yeah, you're on black
I can't see
holes.
I can't see nothing. This is not good. All right, I need to Control Delete Task Manager. That was a good way to get out of that. I don't know what happened there. My screen just went completely black.
It's weird.
I think it was the annotation thing crashed. There we go. Okay. So basically, that little digression was basically, I was saying that as strange as this is, the fact that ripples in space and time can travel out from two colliding black holes kind of proves that Einstein was correct. And there's a whole bunch of different reasons why we know Einstein was correct in this. As a matter of fact, your GPS would not work correctly without taking into account Einstein's theory of gravity. Black holes. So what happens if a star collapses? The gravity gets so strong that not even light can escape, and the space gets warped in on itself so tightly that light can't even escape from that event horizon. So it's when a star becomes too compact. So anything in its vicinity will be attracted by this warped space-time and lost. Here's a good question. What would happen if the Earth, to the Earth, if the sun became a black hole right now? What would happen? Pick the best answer. This is a tricky question. About 30 more seconds for everybody else to. Yeah, nobody got it right. It's none of the above. What would happen is the Earth would continue to orbit around the black hole just like it orbited around the sun. So there's no more mass invented or created out of nothing. And we're still following Newton's universal law of gravitation. So that would be the mass of the sun, and this would be the mass of the earth. The distance between them. This does not change. The mass of the sun doesn't change, and the mass of the earth doesn't change. So the force doesn't change. So none of these answers like really reflect that. It wouldn't break away because in order to break away from the attraction of the sun, the force would have to go to 0, and that doesn't happen. It wouldn't be pulled into the sun because you would have to assume that there's more mass either in the earth or the sun, and that doesn't happen. It wouldn't become a black hole too. I don't know if black holes are contagious. Maybe that's what nobody picked that one. So that's good. So the correct answer is none of the above. Wormhole is like kind of they probably don't exist. It's just a theoretical possibility if you do the math with Einstein's general relativity. And it's basically a tunnel of space and time. So possible, but not likely. Okay. So universal gravity applied to this, everything is acting on everything else. The earth is round because of gravity, because all the parts are basically being pulled in toward the center of the earth. So it's not exactly round because it's spinning. It's a little bit fatter at the equator because of its rotational motion. So the universe is expanding and accelerating outwards since the Big Bang. And that is the last slide. Sharing. All right, guys, did you guys have any questions?
I have a question.
Yeah.
Are we gonna have a lab this upcoming week?
Next week, yes.
Okay, thank you.
Is that what you're referring to?
Yes.
And Alexia, you sent me an email, right?
Yes, I did.
You sent me an email?
Yes, I did.
Yeah, I got that. I put a little star on it to remember. When do you need
Okay.
that by? When do you need that by?
Maybe this weekend.
Okay.
Yeah.
All right.
Maybe by Saturday, Sunday.
Yeah. So here, I'm going to give since this is such a small group, don't share this with the whole class, but I'll give everybody my cell phone number so you can text me. So take that down. So if I forget something, like, you need to get a hold of me or whatever, and I'm not responding to my email, shoot me a text. I'm okay with that.
Thank you. Did you see
Yeah.
the email I first emailed? Because what I did was I forwarded it to your personal email afterwards. Was that the right one?
Yeah. I responded to that one quicker. I got a new laptop and I have Windows on this laptop. So because the school district uses Microsoft Outlook, I get notifications because I used it to sign in. So it's working pretty good. But it's probably still better to send to my personal email. But if for whatever reason I don't respond and you need something fairly urgently, just
Okay.
and that goes the same. Like I haven't. The first semester we did this. This is our third semester in distance learning. The first semester I got distracted doing something. Like I knew there was class earlier in the morning, but I just, for whatever reason, I spaced it out. So if that ever happens, hopefully that doesn't happen. Then just shoot me a text. Okay. All right, guys. You guys have a great rest of the day.
Thank
I
you.
can stop there.